My name is Michael Goldfarb, and I was asked to come and present to you some of the work that my research group does in the development of assistive devices to improve quality of life for people with physical disabilities. And our group is in part biomechanics, based in biomechanics, or the work that we do is in part based in biomechanics and in part based in robotics. And by the way, feel free to stop and ask questions at any point if there's something that you want to ask about. What I was going to talk about today are three of the projects that we're working on, which are the one is the development of a robotic leg to enhance mobility for lower extremity amputees. One is the development of what we call a multi-grasp hand, or robotic hand, to enhance functionality for upper extremity amputees. And then the third one is the development of a lower limb exoskeleton to facilitate or enable legged mobility for people with paraplegia. And so I'll talk about these things in this order. So we'll start with the leg, and I'm going to start that by providing just a little bit of background. What I have shown here is a typical, although advanced, commercially available lower limb prosthesis. And one thing that's uniformly the case with current commercially available lower limb prostheses is that they are energetically passive devices. And what that means is they can't produce power. They don't have the equivalent of muscles in the leg. Because they can't produce power, because they don't have the equivalent of muscles, they're obviously pretty limited with respect to their ability to reproduce the functionality of the healthy limb. So it's only been relatively recently, as in within the past 5 years or so, that robotics technology has become good enough to actually put power into an artificial leg. And in particular, the advances in microelectronics, advances in lithium-ion and lithium polymer batteries, advances in the power density of rare earth magnet brushless motors, all those kind of things kind of came together in the last 5 years or so and make it possible to build a leg that has biomechanical levels of torque and power at the joints, and yet is small enough and light enough to fit within the size and weight constraints of a healthy limb. So if one can do that, in other words, if you could actually put muscles into an artificial leg, then of course it seems obvious that you could much better reproduce the functionality of the healthy limb. And so that's what my group did. Starting about 2005, we recognized that this was a possibility, and were funded with some proposals to build a powered leg and determine whether or not it provided substantial benefits relative to the commercial passive type prosthesis. So this was the first, and is still, as far as we know, is the only robotic leg with a fully powered knee joint and ankle joint. This was our first generation. Now we did a lot of work with this, and then we've more recently built a second generation device. This has a motor here to power the knee, a motor here to power the ankle. It has a battery that's encased in the structure, so you can't really see it. It has a number of sensors on it, and the sensors are important for reasons I'll mention in a little bit, but the sensors determine the configuration of the leg, the orientation and the configuration of the leg also in space, so relative to the ground, and also the sensors to determine how much load a person has on the leg at any time. In other words, how much weight they're bearing on the leg. It has microcontrollers, which are obviously important for control, and I'll discuss that in a little bit. And the leg weighs a little bit over 9 pounds, which, to put that in perspective, is the weight of an equivalent healthy limb of a person that weighs 105 pounds. So it's relatively light for reproducing the functionality of a healthy limb. Okay, so I mentioned some about the sensors and the microcontrollers, and they are necessary in order to control a powered prosthesis. I implied before that the reason why legs had not historically or traditionally had power or the equivalent of muscles is because the robotics technology wasn't sufficiently mature, which is the case. But there's also a secondary reason, which is has to do with control. With a passive leg fundamentally can only react to what a person does. It fundamentally cannot move itself. So it's limited in what it can do, but consequently, if it fundamentally can't move itself, then there's no risk that it's ever going to do anything that the user doesn't want it to do. Once you put power in a leg, once you make a robotic leg, then there is the possibility, if the controller is not set up right, that the leg could do something that person doesn't want it to do. So while I'm standing here, if for some reason the leg decides I'm wearing a powered leg, a robotic artificial leg, and it decides I want to start walking or running or stair climbing, then it could do that. And so obviously that's not something I wanted to do. So in order to feasibly implement a robotic leg, it really changes the paradigm of prosthetics. You now have to have a system with sensors, with a controller that has to understand what it is that the person wants it to do, and it has to do that safely and reliably, and what we call implicitly, which means that it just should be natural. A person shouldn't have to do anything strange to operate the leg. And so I'm not going to go into the details of the controller we developed, but our research group, probably for the first several years of our work in this, focused just on the controller and how to do that. And we'd since developed control methods that use all the sensors on the leg and are constantly monitoring the sensors. And based on patterns that the sensors see, the leg infers what it's supposed to do. In other words, infers what the user wants it to do, and it does that activity. Another thing that's very important is in constantly monitoring those patterns, if it ever sees those patterns, let's say, either kind of go dead or that's a little bit of a simplification, but go to a state where it's clear that the person doesn't want to continue moving, then the device defaults to a passive leg. So in other words, something that's not going to move unless the person actually excites it to move. So it's a controller that's fundamentally safe and natural and provides significantly enhanced biomechanics. And so rather than explain how the controller works, by the way, if one is interested in how the controller works, which is more of a topic of control theory than biomechanics per se, but well, let's say some combination of control theory and biomechanics. But there are papers that we have that you can look to see how that works. But rather than talk about how it works, I'm just going to show some of the kind of results of how it works. So what this shows, this is a video, and it will show that Generation 1 powered leg on a above-knee amputee, and it's showing the amputee walking at 3 cadences, first in real time and then in slow motion. So that was slow. This is self-selected, so this would kind of be like a natural walking pace. This is the slow motion version of self-selected. And a few things to look at are here, biomechanically, that's called the loading response. And then you can see in late stance there was something called push-off. This is fast, so you can see it a little bit better. I'll point these out. The loading response is at heel strike, where the leg acts like a shock absorber, and then push-off is in late stance, where the leg basically propels the user and itself forward. I'll mention that, or I'll touch on that again in a minute. But first, let's look at essentially the same thing you just saw, but in maybe some more kind of quantitative terms. So let me explain what all this is. First, just look at the top row. So these two plots. And these two plots are for healthy individuals. It's the average of a number of healthy individuals. But this is for level walking at 3 different speeds. And this is the knee angle versus stride and the ankle angle versus stride. And gait is a periodic activity, so you often just look at one period of activity. And that is called a stride. And that starts at heel strike for this leg. And then so in this part, the leg is in stance phase. The foot's on the ground. And then you have here, starting about here, the swing phase where the foot's in the air, and then it heel strikes again. So heel strike to heel strike. This is the knee angle versus stride and the ankle angle versus stride. This middle row is the powered prosthesis. So this is data corresponding to the video that you just saw. And then at the bottom, this is for a state-of-the-art passive prosthesis. So this is actually for the prosthesis that you saw that I showed on my introductory slide about the commercial prostheses. And so some things to point out about this data. It's kind of a lot to take in, but basically the essence of it is that this looks like this, right? The power prosthesis biomechanics looks like the healthy limb biomechanics. The passive prosthesis biomechanics looks considerably less like the healthy limb, so it's much more limited in its ability to reproduce healthy biomechanical behavior. If you look at the ankle, this basically looks like this, whereas this looks much less, or is missing a lot of the key features of the healthy movement. Some more specific things. I mentioned loading response. Loading response is when your knee and ankle together act like a shock absorber at heel strike, and there's lots of purposes for that, but including decreasing the impact on your joints and also minimizing the likelihood of slip are a couple reasons why, a couple of the functions of loading response. But you see here that slight knee flexion, slight ankle dorsiflexion, that's loading response. You get that same behavior, as I pointed out in the video, you get that same behavior in the power prosthesis, and that behavior is essentially absent. I mean, almost totally absent from the passive prosthesis. Another important feature that I pointed out is push-off. So here's push-off, this rapid ankle plantar flexion as you move forward at the end of stance. Push-off in healthy, this is push-off in the power prosthesis, and that's kind of missing completely from the passive prosthesis because it's passive. It doesn't have power, doesn't have the ability to push off. As I mentioned, it effectively doesn't have muscles. So some benefits of power of push-off. Why would you want push-off? Basically, what push-off does in walking, it has two functions. The first is it propels the center of mass of the body forward. That's in early push-off. In the latter part of push-off, instead of propelling the body center of mass forward, it propels the swing leg forward and imparts momentum to it, so you get this healthy, robust swing. Amputees don't have push-off. What they do instead is they sling the leg forward with their hip. So the leg's passive, and so they have to do a big slinging motion with their hip to get their leg forward. And so consequently, they expend a lot more energy in level walking, and they have a relatively weak swing. It's pretty common to see amputees do what's called vaulting on their sound side. So as they swing this forward, then they go up on their toe on their sound side to clear the leg so they don't stumble because they don't have much, they don't have a very robust swing. So some of the measured benefits of having power in the leg versus not having power that we've measured is the subjects on whom we've measured this walk on average 24% faster. They walk faster with the powered leg relative to the passive leg. That makes sense. It's contributing power. It's pushing them off. It's making it easier for them to walk. The other thing it does is reduce considerably the amount of energy it takes for them to walk. So they require, depending on how you measure this, somewhere between 23 or 39% more energy to walk with that passive leg compared to walking with the powered leg. Now that makes sense because the powered leg, again, has muscles. It helps move you forward. It also has muscles that are self-powered. It has a battery powering those muscles, so it's giving you energy that is not coming from your metabolic system. Okay, that's all level walking, and it turns out that these passive legs are not really, I mean, they're not that bad at level walking. I pointed out data that indicates they're not that great, but they're also not that bad. But they're basically tuned to level walking. So once you start doing other things, like going up slopes, down slopes, upstairs, downstairs, and even standing and moving on uneven terrain, then they get much worse. And so there's lots of different types of, okay. Conversely, if you have a fully robotic leg, and I mentioned that changes completely the paradigm of how these legs work because you're using an intelligent controller to infer what the leg's supposed to do. So anything it can infer, it can do. So if you have enough sensors to identify whether a person's walking upslope, downslope, upstairs, downstairs, which we do, then you can provide that with biomechanics. So I don't have time in the talk to go through a lot of different examples, but I'm going to go through at least and show walking up slopes. So as an example of how a powered leg compares to a robotic leg compares to a passive leg. So this data is laid out in a similar way to the data I showed before, where the top row is healthy. This is knee angle versus stride, ankle angle versus stride for healthy individuals But instead of different speeds, now we have 3 different slopes. Well, this is level, dark blue, and then up 5 degrees and up 10 degree slope. And then this is the powered prosthesis, this is the passive prosthesis. Okay, and some things, there's a lot to see on this, so I will point this out. One of the major differences is when you heel strike going up a slope, your knee is bent. And by the time you push off, your knee is almost straight. So there's a net knee extension. And that makes sense because I'll demonstrate a little bit, but the slope, the ground in front of you is higher than the ground behind you, so you're probably going to have a bent knee. But the other reason to heel strike with a bent knee is, it's hard for me to demonstrate without a slope, but I have to, going up the slope, you have to lift your body center mass up the slope. And so my knee starts bent, and as I go through stance, my knee straightens, and that net knee extension is lifting my body center mass up the slope. So that's actually having to generate power to lift you up the slope. Now, of course, a passive leg can't do that, but a healthy leg, you can see this net knee extension. The powered prosthesis, you can see the same net knee extension. So the prosthesis is providing the energy or the power to lift a person up the slope. And you can't get that in the passive prosthesis because it has no power. So if you heel strike with a bent knee, you can't get the knee straight during stance. So you heel strike instead with a straight knee and just keep it straight the whole time. So that's a major difference. I mentioned the other part of power push-off, the other function is to initiate a robust swing phase. So you can see the swing phase in the power prosthesis looks very similar to the swing phase in healthy, but the swing phase is much weaker in the passive prosthesis because you don't have push-off. Another thing, one of the things the ankle does is, whenever we walk, it's easiest to stabilize yourself, to balance yourself, if your body is aligned with gravity. And I can kind of do it with my body's not aligned with gravity, but it's harder. It requires more energy, and I'm less stable. So if you're walking up a slope, your ankle is going to dorsiflex in proportion to the slope to keep your body aligned with gravity. Healthy, you can see that in healthy biomechanics. You see that in the powered prosthesis, but that's absent from the passive prosthesis. You also see this powered push-off I mentioned before. Of course, absence of it there. So here's a pictorial way of looking at the same thing. So if we start first with the bottom row, this is a passive prosthesis walking up a 10-degree slope. And here, you can't see this, but there is no powered push-off. You can see that the amputee is on his toe, on his sound side. And he has to be on his toe because swing phase is really weak because you don't have powered push-off and you have the slope. And so if he's not on his toe, he's at high risk of scuffing or stumbling, which can lead to a fall because he doesn't have muscles in his leg then to actively extend his knee if he stumbles on it. So you can see heel striking has to be with that straight knee because, as I mentioned, if the knee's not straight, when it hits the ground, you can't straighten it. The powered leg, on the other hand, on top, you can't visually see, but there is powered push-off. You can see he's flat on his foot here, no vaulting, because he has a robust swing phase. And then when he heel strikes, he has a bent knee, which is kind of the biomechanically normal or natural thing to do. Yes, question?
So if someone does stumble with the powered prosthesis, are they able to hold themselves up?
Yeah, it's a good question. So the question was, if somebody stumbles with a passive prosthesis, then are they able to hold themselves up? And for the most part, the answer is no. And I'm going to, in a couple slides, I get to that, because just to kind of preempt what I'm going to say. But the falling is a really big problem with amputees. Amputees fall a lot. And I'll get to that in a little bit. But there are, and part of the reason they fall, there's multiple reasons, but one is the inadequacy of passive prostheses. Once you have a robotic prosthesis, if you recognized you stumbled, you can do a much better job of recovering from it. So we'll get to that in a minute. This is a video version of the same kind of the pictures I just showed. Actually, this is a passive prosthesis. So look at his sound side. He's vaulting, he's having to sling that forward. All right, that's walking up a 10-degree slope with a passive prosthesis. With the powered prosthesis, then both legs are contributing to going up the slope, and so you don't see that nearly as much asymmetry in the walking. And energetically, we haven't done these measurements, but based on what our subjects report to us, there's a gigantic difference energetically in the energy cost of walking up a slope. Okay, this is what I was just going to get to. Falls are a huge deal. The amputees fall at the same rate as the institution living elderly. They seek medical attention at the same rate. The problem is worse in younger amputees than in older amputees because younger amputees are less intimidated by challenging terrain. An older amputee in general is just going to walk on a flat surface, not going to deal with anything more challenging. There's lots of things we can do here, but some of what we're starting to do is stumble recovery reflexes. And so you can see if we have sensors, we can figure out when a person stumbled, and then we have the power. A stumble recovery reflex is fundamentally an active reflex. You can't do it passively. But the purpose of it, of course, is this is kind of in a biomechanics way. Once you stumble, then you impart this forward angular momentum to your whole body, and you need therefore to reach your leg out in front of you in order to what's called arrest that forward angular momentum or keep yourself from face planting. And so that's effectively what we can implement here. And so this is pretty early work, not yet published work, but something that is potentially really valuable. I kind of think of it as ABS, like anti-lock brakes for amputees. Okay. The work in my lab, the whole purpose of what we do is to enhance quality of life for people with physical disabilities, and you can't do that. Well, I should hedge what I say a little bit. The most direct way of doing that is to make devices or products that are available for people to buy and to use. And so that's one of the strong motivations in my group. And so with each of these things I'm talking about, when we develop something that can effectively improve quality of life, then we seek commercial partners to make it available on the market. And so in this case, we have licensed the intellectual property and the technology associated with the robotic leg to a California company called Freedom Innovations. They are one of the largest U.S. manufacturers of high-tech lower limb prostheses, and they are in the process of transitioning this into a product. This now looks different than the other one I showed. This is the Generation 2 version, and the Generation 2 version, the Generation 1 version was used to kind of prove out all the concepts. Generation 2 was developed to be more commercially feasible. So you can see we've since developed the Generation 2, and then this I didn't show before just because of the lack of time, but this is one of the things that you put this leg on amputees, and walking, they say, yeah, that's better, but something like this, stair ascent, and even stair descent is a huge difference to them. Same with slope ascent and descent. So that's some of the functionality that the leg can provide. All right, so, okay, another one. I actually forgot about this slide, but more functionality that you can get from a robotic leg that you can't get from a passive leg is running, biomechanically kind of proper running. You may have seen amputees that can run with certain carbon fiber legs, and they can run effectively with those, but you can't use those for walking, and you can't use those for sitting. You put on one of those legs when you're on a track and you're about to run a race, and it's hard to even stand in those. In general, you have to move around to balance on them. So what one can do with the robotic leg is have a leg somebody can use in their daily life, and it can adapt to all these different activities. So, for example, when you are late, when you're in a train station wanting to catch a train or a plane or a bus, and you're late, you can run and catch the bus. Or if you are watching a kid and the kid runs out in the street, or if you're in the street and you need to get out of the street, you can basically just transition to running on this, and it gives you that improved mobility. And this particular amputee, who happens to be a nursing student here, master's student in nursing school here at Vanderbilt, but we asked him what he does when he's late for a bus, and he says he misses it. So anyway, so this can offer some enhanced functionality, enhanced mobility, and hopefully improve quality of life for people. We're hoping, by the way, that leg is on the market in 2014. That's the target for this company that's developing it, or that's translating it to market. So I mentioned at the beginning, I was going to talk about three topics. There is the robotic lower limb prostheses, and then there's also we're developing robotic upper extremity prostheses. And in particular, although we're developing different parts of the arm, I'm just going to focus on the hand today. If you look at the commercial state of the art, there's really two options. This seems archaic, but it's really not. A lot of people use what are called body-powered prostheses. They have a harness that has a cable. You wear it around your shoulders. Usually you have a split hook with a cable going to it, a set of rubber bands or elastic bands that close it, and you kind of shrug your shoulders down to open it up, and when you relax your shoulders, well, you shrug your shoulders down, it pulls on the cable, it opens it up, and when you relax your shoulders, then the rubber bands close it. Seems archaic, but used by a lot of people. And then there's kind of the more technologically advanced version, which is called myoelectric. These are various myoelectric hands. This is kind of a quasi-hand. But these work by putting electrodes on your, if you're a transradial amputee, the electrodes go on your forearm, one on each side of the forearm, the anterior and posterior aspects of your forearm. And as you all probably know, when your muscles contract, it gives off an electrical signal. Your whole body gives off electrical signals, different parts of your body, your heart and your brain, but at any rate, your muscles do as well. And you can pick up those signals from the surface of your skin. It's called EMG, electromyogram, and use those signals to drive open or close an electric motor. So even if I'm an amputee, I don't have, I still have musculature in the residual limb, and it's not moving anything, but I still have it. I can still contract it, and I can use those to basically drive one of these hands. But one of the things that's universally true, or has been universally true about these hands, is their single degree of freedom. They might look like they have multiple fingers, but all they do is open and close. And so that's one thing that certainly ties all current technology together, is they're all single degree of freedom devices. And when you look at our hands, they obviously, they have many more degrees of freedom than that. They have somewhere north of 20 degrees of freedom, depending on how you count things. So one of the things that we've developed, and this has been enabled by the same advances in robotics technology I mentioned before for the leg, is what we call a multi-grasp hand prosthesis. In other words, something that doesn't just open and close, but can achieve a number of different postures. In fact, the target set of postures that we selected are these 8. Well, I call them postures. Some are postures, some are grasps. There are actually 2 postures here, which are platform and point. And then there are 3 whole hand grasps, which are the hook grasp, like carrying a briefcase or backpack or suitcase. There is a tripod grasp, and then there's, spherical and cylindrical. Spherical, cylindrical, and hook. Those are the 3 that I call whole hand grasps. And then there are 3 which are called precision grasps, and those are lateral pinch, like if you'd hold a key to turn a key in something, tip, as you can see here, picking up something small, and then tripod, which is just like a tip, but a slightly more stable version of a tip. So if you look at the biomechanics literature in in activities of daily living for your arms and your hands, then this set covers somewhere north of 85 to 90% of the activities of daily living. So this was, in our opinion, the right set to enable. And so what we did is chose a minimum number of actuators, in other words, separate motors, to achieve that set. And so we do that with 4 actuators. Each of these is an actuation unit. And basically, one moves the thumb back and forth directly, one moves the thumb in flexion directly, one moves the forefinger in flexion directly, and then the other moves all 3 of these together in a coupled way, but they're on a differential, so if you hold one back, the other 2 can grasp. And the reason for that is that the thumb and the forefinger are basically used in those precision grasps, and you want precision control of those. We also have bidirectional control of those, so you can forcibly open and forcibly close them. These 3 are basically there to stabilize grasps. And so if they can just wrap around whatever object you're holding, then they're doing largely what their function is. We have that kind of distribution of actuation. We characterize this, and this isn't worth going over too much, other than to say that these are, again, if you go back to that biomechanics literature and see what kind of speeds and forces you need on your digits to do activities of daily living, this hand that we've developed more than covers everything up to the tasks that require the most force in activities of daily living, as characterized by the papers that we have access to, are pushing a plug, an electric plug into a socket, or pulling it out of a socket. And then second to that, there are things like zippering a suitcase and whatnot. But at any rate, the hand that we developed can do all of those things as far as force and movement. So we have biomechanical levels of force and movement. In other words, it would be useful if, and this is kind of, there's a thread that runs through some of the things that we do, which has to do with control. useful if a person can control it and access all those grasp and postures in a reliable, intuitive manner that doesn't require significant cognition. So one would think that maybe if you can develop a hand that can move in lots of different ways, that's fundamentally better than developing a hand that can just open and close. But the problem is you have to control it. And this is pretty easy to control because you've got an electrode here and an electrode here, and one opens and one closes. So I don't have to think a lot about using it. But this question is, well, here's the thing. If I have to think a lot about using these postures, then somebody's not going to use them. Somebody would rather have something that doesn't functionally do as much, but it's easy to control, than something that functionally can do a lot, but it's really challenging to control. So a key to the effective implementation of this kind of technology is figuring out how to interface it with the person such that they can control it in an intuitive, effective manner. And by the way, it wasn't our assumption that, it wasn't our assumption that this was necessarily better than this. So well, I shouldn't say that. It was a hypothesis, but we want to demonstrate that. So as you'll see, we've developed a controller, which I'll talk about, and what we're in the process of doing right now is comparing somebody's ability to do activities of daily living with this versus this. So I'll talk about that in a second. But as far as how to control it, the big change that we made between the way traditional prostheses have been controlled with the myoelectric interface. This is the myoelectric interface I was talking about, an electrode, a surface electrode on either side. These are usually embedded into the socket. So you don't have to put electrodes on. You just slide your socket on, and the electrodes are built in. So this is just to demonstrate, though. In the research lab, we just do it with sticky electrodes. When we do it with amputee subjects, then we just use what's in their socket. But this is the big difference that we did, is that we embedded a lot of low-level intelligence in the hand. So in the hand, we measure the motion, the configuration of the hand, and we measure the force of interaction. And based on those things, the hand can do a lot of coordination on its own. It's just the same way that it happens in our body. You know, we have the medulla oblongata and cerebellum, and they take care of a lot of the low-level things. We don't think about it. So when I want to pick something up, I just think essentially I might pre-position my thumb based on the type of object. And other than that, I just close around the object, and your sensors, your low-level loops, do all the rest for you. And so we've set up a controller, and I won't go into it too much, which effectively does the same thing. You pre-plan, which is a normal biomechanical thing to do. You pre-plan your grasp by positioning your thumb one way or the other. Once you do that, all you think is close or open, and all the rest, the control of those 4 actuators and sequencing of those, it's all handled by low-level coordination. So I'll show you here a video. Yeah, yes. Let me pause this video.
With like hand prosthetics, is that like they can't feel like how hard they're squeezing?
Yeah, that's a good question. So the question was, the one limitation is lack of sensation, and that's true, and we're not addressing that, right? But it's an important issue to be addressed, and these kind of changes, advances in prosthetics, is a field that has gained a lot of momentum in the last few years, and will continue. There'll be a lot of continued rapid changes in this field over the next couple decades, and providing sensory information for somebody is a huge part of that, but not something that our group's working on directly. So okay, this is a video demonstration of these things, of how this controller works. All of these are internal sensory information that the hand's making its own decisions on. All that the person is doing is either flexion or extension. All right, so either by flexion or extension and pre-positioning the thumb, that you can achieve all these different postures, and you do it in a natural, intuitive way. This is kind of just a slow motion version of the same. So you can see a person flexes their extensor muscles, and you go through this sequence, and you flex both at the same time. It repositions your thumb, and then you flex. You go through flexion, and it takes you through these different postures. So if somebody's interested in this, there are also recent papers that have been submitted on that describe a little bit more. But as I mentioned, one doesn't want to assume that fancier is better, and so you need to do an objective functional assessment. And that's what we're doing now. We're doing something, this test was developed by a university in England. It's called the Southampton Assessment Procedure, and it consists of a battery of these 26 different tests which are reflective of activities of daily living and all these different grasps. And as you can see, you time what you do. And so this is an amputee wearing this prosthesis, and you can see going through this Southampton Assessment Procedure. This simulates cutting, and there's doing zippers, and there's turning keys, and there's using a screwdriver, and taking a lid off of a jar. So, pouring. There's a number of different tests that are used, but so this is a universal test, and it's been demonstrated to have good repeatability, reliability, and so on and so forth. One thing you can see about this amputee that makes it challenging for him actually when he has to do bimanual tasks is he's a bilateral amputee, so he has a traditional single grasp prosthesis on his other hand. But if you look at the preliminary results, we are in the process of doing 3 amputees. If you look at preliminary results, this is kind of a lot of numbers to look at, but these are. There was a paper published in 2010 in Europe that used the same test on a standard single grasp myoelectric prosthesis and a multi-grasp prosthesis that is emerging that's a good prosthesis but doesn't have really a multi-grasp controller to go with it. And this is our hand in that test that you just saw. So we're scoring an 81. By the way, something between 90 and 100 would be healthy function. We're scoring an 81 on this test. The single grasp prosthesis, this is a different user, but scored 74, and then with the multi-grasp without really an appropriate controller scored 52. So far, it looks like we have considerably better functionality, although this is early, so we need to continue to complete these tests. As I mentioned before, one of the things we try to do is make sure our work is commercially translated so people can use it. And so there is a company based in Washington State called Orthocare Innovations that has licensed this, and they're working with us. We're working with them for the commercial translation of this technology. So the third topic I am going to talk about, is exoskeletons, lower limb exoskeletons for people with paraplegia. And same advances in robotics have enabled this. This is an exoskeleton that our research group has built and is testing. Actually, we were testing it yesterday, with a different subject. But so one of the things about this is that this is for paraplegics, people who are completely paralyzed from the, let's say, waist below or chest below. It requires stability aids because we can't stabilize a person if we can only control movement in this plane, which is what we're doing. And so this isn't supposed to replace a wheelchair for mobility, but it does a lot of other things. There's a lot of physiological benefits that come from standing and walking. Paraplegics who are confined to sitting permanently have a lot of secondary physiological issues that go along with that. So there's a lot of demonstrated physiological benefits. There's clear psychological benefits and documented psychological benefits to standing and walking. And then there's also the access to mobility access to places that are not easily accessible by a wheelchair. And there are a lot of those places, a lot more than one would think. So it provides several different benefits. The layout of ours is we have a battery encased in the hip piece in the back, a pair of motors, a motor that drives the knee joint through a transmission, a motor that drives the hip joint through a transmission, and then all the kind of, we've got a couple set of embedded electronics that are encased in the thigh, and then the two legs talk to each other through a communication, through a set of communication channels that go through the hip. We made it so that you can snap it apart into 3 pieces, and there's a few reasons we do that. One is because, as I said, it's not really going to replace a wheelchair for mobility, but one would imagine that it would be most useful if you could pack it into a case, put it on the back of your wheelchair, and wheel to wheel to a park and get out, snap it on, and walk around, or to a movie theater or whatnot. And so we have this modular design, both so somebody can take it with them, and so somebody can put it on and take it off by themselves and do it in a fairly easy way. Control is another issue. Of course, I've talked about that in all of our projects. It is a big issue. In this case, the question is how somebody tells the device what to do, because you can't move your legs, and you don't want push buttons, because, among other things, your hands are on crutches. So we could have instrumented the crutches and put push buttons on them, but we didn't think that was a good idea. So instead, effectively, what we do is we have enough sensors on the exoskeleton itself to understand the configuration of the person and understand where their center of pressure is. And they can move their center of pressure around by using the crutches against the ground. So effectively what we have is something like a legged Segway, where a person, when they're standing and they want to walk forward, they use their crutches to lean themselves forward, and that basically means they want to take a step. And if they continue in that forward lean, they continue walking. If they stand upright, then they'll stop walking, and so on. If you're standing and you lean backward with your crutches, that means the system you want to sit, and so on. So it infers, based on your current state and where your center of pressure is lying, it infers what it's supposed to do. So this is a video that obviously doesn't have a person in it, but you can kind of see leaning it forward, it walks, straightening it up, it doesn't. Now, one of the things you may or may not have seen is when he first leaned it forward, it started kind of vibrating. It also uses that as information to the person, kind of like the way your cell phone vibrates, to say, if you keep leaning forward, you're about to take a step. It doesn't do that every step, just on the first time. Whenever you change activities, it does that. So this is all right. This is a paraplegic. He's completely paralyzed from the waist down. This is a rehab facility that's in Franklin, about 20 minutes south of here. In order to stand up, he had to put his body into a certain configuration that said he's ready to stand. Then he had to push up a little bit with his crutches, and that told the system that he was ready to stand, and it kicked in and stood him up. This one, again, the way he's leaning his body by using the crutches is telling the system what to do. This is the guy that we were working with yesterday, but this video is from a couple months ago. I will, he's turning. I'm going to just forward it a little bit. Okay, so one of the things, to then come to standing, you can see he paused. And if he pauses for about 2 seconds, and the system will give him a little vibration that say, okay, your next step isn't a step forward, but just a step to make you stand. Because once he's in standing, then he can use his crutches and position himself in front of the chair, and then lean back. When he leans back, again, he'll get that vibration once he's met the condition for sitting. If he continues to hold that, then he'll sit. So this system, that guy, by the way, played football at MTSU. He was just injured maybe 2 years ago. I mean, he's about 40 now, but when he was in college, he was playing football. This is just, I think I have enough time. Well, I'll tell you what. We'll let him stand and take a few steps. This is just same system walking outside. Different subject. We work with a hospital called the Shepherd Center, which has its main facility in Atlanta and a satellite facility in Franklin, Tennessee. So we work with both of those. In fact, we'll be on Monday. We're going to the Shepherd Center to do more experiments with more subjects. All right. Another thing that we've done is program in stair ascent and stair descent. And so in order to do this, you're now leaning not just forward, but you're leaning forward and to the side, and that tells the system that you want to go into a stair ascent mode. And then once you're in that mode, you don't have to continue leaning to the side. You just lean forward. You have to do it twice. Lean forward the first time, put one leg up on the stair, lean forward the second time to put the other leg up on the stair. And then so walking downstairs would be somewhat similar. As I've said with the other technologies, it's our intention when we develop something to make it available. So this technology has been licensed to a company called Parker Hannifin. This is subject in one of the subject that's one of our subjects in Atlanta. This is the CTO of Parker, and this is the lead engineer on that project. So it's just licensed to Parker, and we're working with Parker and with the Shepherd Center to start clinical trials, and they expect to have a commercial version on the market in 2014. So we're working with them to make that happen. And then finally, my last slide is all of this stuff was done by a research group. Our group happens to be located in Olin Hall, but these are all the people who contributed to various aspects of those projects. So that was my talk. If you all have questions, then I'd be happy to answer any. Yes?
How much would something like that cost?
Yeah, okay, that's a good question. The question was, how much would something like that cost? And that's a relevant question for all three of those projects. So I assume your question was aimed primarily at the exoskeleton, though. Maybe it was, maybe it's not. This stuff is not terribly expensive anymore. I think it's very much like software, where most of the cost is in the development of the device. It's not super cheap to make to develop these, but most of the cost is in the development. The development in this case has been all with federal funds, and so the company doesn't have to recoup those development costs, so they can make it available cheaper. So kind of to more directly answer your question is when we licensed these various things, there were multiple companies interested. And with the exoskeleton in particular, one of the reasons we chose Parker is that they have an immense amount of manufacturing resources, and they can leverage those resources. They're a global company with manufacturing facilities all over the world. Actually, what they do is, if any commercial aircraft you fly on these days, the flight control systems are made by Parker. So this is kind of this healthcare industry is a new thing they're getting into. They're very enthusiastic about it, but they want to leverage essentially all of their infrastructure, automation infrastructure, to be able to make these and make them available at a very affordable cost. So they have spoken with me. I've spoken with the CTO about how much this will cost. I can't give you that number, but that number is a fraction of. There's some other emerging technologies that are similar to this that have started to emerge over the last couple years, and the price tag on those is in the high tens of thousands of dollars, and the price tag on this that we have talked about, and they believe they will bring it to market for, is probably a fifth of what these other companies are talking about, and so that will therefore then put kind of this downward price pressure on the whole market and make this technology much more affordable. So what they talked about, basically, I think I can say this and not overcommit, is one of these would sell for essentially the same cost of a high-end bicycle. That's what we're talking about. But it's a good question. It's an important question, because we want to improve quality of life of people. You can't do that if people can't afford it. Okay. All right. Well, thanks. And I'm around. I'm around if people have questions in the future.